So today, the guild discussion, or as I like to say, guild battle royale. There's been a lot of good discussion on Piazza. I want that to continue, and I want some of that reiteration. There have been plenty of arguments for and against the guild, other languages, what are the approaches, people learning things, that's awesome. So let's talk about the GIL in Python and multiprocessing, multi-threading, other languages, better languages, worse languages. All right, why does Python have a GIL? Is that a hand raise? I saw that. It looked like it. Somebody.
Basically, the way Python is implemented in memory management, like, it basically needs to show that memory management is let's state, so
Yep.
that, so basically, forces an entire interpreter lock so that if multiple threads can access the same state, they don't block each other.
Right. Which, and the memory management in at least CPython implementation is, do you know? Wait, someone? How does Python memory management work? I heard it. Reference counting. Every object has a count of how many other objects see it or how many pointers exist to it. When that count drops to 0, objects are immediately collected. And then it also, that doesn't work in some cases. Reference loops. Basically, if you have a list, you can actually point it back to you can point its tail back to its head. And the reference count of everything is 1, plus maybe some external pointer into it. That gets collected by a generational garbage collector, which we don't need to deal with. But reference counting basically means when I assign a variable to an object, when I say A equals this RDD, the RDD has a reference count. A is a handle to that, it's basically just a name. It increments it by 1. In multi-threaded, if you had, A and B both, if you had 2 objects and you assign them both to the same RDD, its reference count should be 2, but as we saw before, this is a critical section, right? One of them is gonna say, what's the reference count? I need to increment it by 1 and store that back. The other one's gonna say, what's the reference count? Increment it by 1, store it back. If those interleave, I'm gonna end up storing 1, right? One of them's gonna say 0, 0, 1, 1. Thread's bad. And its reference count is now 1, and as soon as one of the handles goes away, it gets collected, even though there's still another handle pointing to it. So you need, for reference counting, thread safety. Why else? Besides memory management, that's a key part. There are other parts. I mean, it was a motivated decision, though. You're correct. It is sort of a historical albatross now, right? It's something that they decided to do it that way. They decided to use reference counting. Although actually the Python collector came a little bit later, I think, in its current implementation. There are a lot of internal structures, right? There are lists. I mean, complicated data structures in Python. You have lists, you have dictionaries, you have sets, you have, that's most of it. And these have internal structure. Oh, there are arrays too, and bit arrays. They have internal structure that you can update in a single iteration. So when you store a value in a dictionary, from the Python's point of view, this is a single instruction. From the bytecode interpreter, it's basically store this value, this key in a dictionary. And in there, you're gonna do some modifications of the internal structure. The data, the dictionary is implemented as a hash table. So storing something might require you to grow the hash table. If someone else comes along and tries to store something in the hash table while it's being updated, bad things are gonna happen. And then there's probably the largest, at this point, historically, the most important reason. So like we said, we hit those first two. Reference counting garbage collector requires thread safety. Every built-in type is thread safe. C extensions can ignore threads, right? If I write C code that I want callable from Python, I put a little wrapper on it. It's not very complicated, it goes into C code. I can have local variables, I can have global state, I can have whatever. And I know that once Python calls into my code, I can just do whatever, and until it leaves my code, unless I give up the GIL myself, I have the GIL, I have a lock. There's no way another thread can jump in there and start messing with it. And this is super powerful, because it makes it so that almost anyone can write a C extension to Python. It doesn't take that long. With Python, it's really easy. If you have C code that you want to wrap, Python, it takes you, a couple hours, and you can wrap it and basically put that out there as, hey, here's a Python extension, right? It's like, it's really quite trivial once you learn the tools. Very thin wrapper. No worries about threading. If I did this for, I don't know, Go or something that has a lot of threading, I would have to be very knowledgeable about how things might enter in there. And so this is why the GIL will never go away, because there's a huge baggage. I mean, the number of Python extensions that are just regularly used by everyone, NumPy and everything else, this assumption is very strong and just baked in there, and it would be useless to get rid of the GIL. You basically have Python without the batteries. Have you heard this phrase about Python? Python's key phrase is batteries included. There's a web server in there, there's an email client in there, there's a diff tool in there, there's a whole bunch of stuff. Like, everything's just in there. And then there are some packages like NumPy and stuff that are very easy to add, so they're almost included. But if you do this, then suddenly you lose that entire support, right? It's just gone. And now you just have a language with funny indentation and nothing you can do with it. Right? That's why I go. These are all sort of justifications. Some of them originally motivated, and some of them now we're stuck with it. Right? Why is it a problem? What's bad about the GIL? Come on, this is your chance. Oh, I wanted to do a poll, actually, before we get farther. Favorite language? Who has one that's not Python? Come on, come on. You're not going to get... What? C++? Awesome. Swift? Okay, that's cool. I know, I don't argue. No, that's cool. That's good. That's good. You like Java? What? Sorry, another one? C? C's good. Especially if you're gonna do like kernel stuff. Other stuff? Anyone? There's a Scala person in here. I know. MATLAB's good. I did a lot of MATLAB. I've done a lot of MATLAB. OCaml? I tried to learn OCaml. I was like, my types are Turing complete. I can't. Like, and it's not just that they're Turing complete, like you have to program them. That's cool. All right. All right, good, good. That's fine. These are all excellent choices, except for Java. No, it's fine too. No, it's all good. Like I said, we're pushing Python in this class, not because Python is the best language, but because it's a fairly common denominator. So, someone coming from MATLAB, someone coming from C++, Java, wherever. A lot of the concepts are similar. It's more pseudocodey. It still allows us, with some very simple tools, to get down to the metal. And so it's sort of a common denominator. But there are plenty of other choices. The nice thing is, in Python in particular, I can wrap all of these languages, right? I can put maybe not like OCaml. I'm not sure what would be required there. But a lot of these languages, Java included, I can build a very simple interface using some of the existing tools and be able to yank code from all the hard work that you guys have done and claim it as my own. Not really, but I didn't want to show you these yet. Don't look. Problems with the GIL. No one said Ruby. What? So old? Like Python's like 80s, right? Yeah, that's pretty old too. It's starting to show it's... By this point, there should be something better. What's wrong with the GIL? What are the problems it causes? What's the main one? Slow. Slow. And but is it multiprocessing, right? Multi-threading, what? Why does that not work? Right, the GIL, you can't do the trick in Java or wherever, it's slow, I'll just use more threads, I'll use more compute, right? And things don't run together at the same time. You only have one piece of interpreted code running at the same time. Python the GIL makes things slower, right? There's no overhead there. It's like, I forget what it is, 20%, even in single-threaded, of time is spent dealing with the GIL. That's lower now. Python 3 has addressed some of that. And it can, it slows things down. I forget the other things. Other problems with the GIL. So this is the thing, yeah, so there was a set of patches, the free threading set of patches, I think that's one of the core Python guys did for a while to experiment with, where he went in and he instead put locks, instead of a global interpreter lock, put locks on all the data structures. So, or possibly had a shared lock for all dictionaries or something like this. So whenever you modified that data structure, it would lock that and then go on. So, so basically split the GIL into tiny pieces. We'll talk more about this later, but basically that's coarse locking versus fine-grained locking, right? The GIL just locks everything, and then while you have the GIL, you can just run. You don't have to worry about locking things in between. When you do fine-grained locking, so the fine-grained locking, there was performance increase then when they had multiple threads, because multiple things could be running. The problem was that in single-threaded programs, you have to still lock, because you don't know if you're multi-threaded, right? And so now you're locking a lot more. You could be locking, if you're dealing with dictionaries a lot, you're gonna be locking almost every instruction, every bytecode instruction. So you're locking and unlocking enough that it dropped performance significantly. And the Python people were basically, that's not good, right? We can't accept that. The performance on single-threaded can't be impacted that much, especially since multiprocessing is one of the most common ways, like actual multiprocessing instead of multi-threading, is one of the most common ways to get better performance out of Python. If you break single-threaded, then you break multiprocessing, all right? So yeah, so that was just a problem. How do, well, there are other ones. Did anyone look up, like David Beasley is a Python programmer. He's really good. He's done some core work, I think. He has some excellent talks on like how broken the GIL can get. He shows things like if you have a spinning compute thread and a waiting I/O thread, the I/O thread can just starve, not able ever to get the CPU. David Beasley, I think I have his name in a slide later. There's some other problems. The GIL is not a scheduler, so priority is left entirely up to the operating system to schedule threads. And so this can lead to other problems where the OS just does there's a poor interaction between information that Python has, like I'm gonna be waiting on a socket, waiting to read data versus I'm gonna be computing, is lost. And if there were more scheduling information, the GIL could take advantage of it. They are starting to add some more things in here. They have some patches that are sort of sitting on the back burner that basically put in some scheduling into the GIL. So it decides which thread is going to run instead of letting the operating system decide. But they're not putting them in because it complicates things, and they actually haven't seen in practice something where an actual real-world case where it happens. There are some sort of benchmarks that show that it's possible. Anyway. All right. Here's where it starts to get a little, like my opinion. How much does the GIL matter? Right? People say, you can easily find comments on the internet to blog posts and things that say the GIL or Stack Overflow questions, where people say the GIL is horrible, it's basically a non-starter. But comments on the internet, don't read the comments. This is my yearly New Year's resolution every year. Don't read the comments, and mostly I manage to stick to it. How much does it really matter? Opinions. Well, this is your chance to argue with me. You get points for arguing with me. How much does it matter? Is it a lot, a little? Does it matter to you? Does it matter to me? When does it matter?
There's a lot of ways to get around the problem that's created, so it doesn't seem like any actuality that it's happening.
Well, that's kind of annoying, right? You're like, if you come to me and say my Python code is slow, and I like to use multi-threading, I'm saying, well, go write a C extension. You're like,
you're using Python, so
you don't have a choice.
you already made that choice.
Oh, you're saying, right. Actually, no, that's really perfect. You're using Python, right? You're using Python. Why are you using Python if you want something to go fast, right? If what you're doing, like for people who went to the seminar by Lyserson, matrix multiply of I forget, it was like a 1K, 4K, I don't remember. It was not a big matrix. 8 hours, like it was like 4K by 4K. I think it was actually smaller than that. I think it was 2K by 2K. 8 hours, right? Something that NumPy does in half a second. Why did you write that in why? Right? Don't do that in Python, don't. That's not gonna be fast that's not gonna be fast in Python, it's not gonna be fast in IronPython, it's not gonna be fast in PyPy. It might be fast in PyPy because of the JIT, because they have this, PyPy is this no-GIL, just-in-time compilation stuff. But in general, why did you write that in Python? This is from the wiki page on the GIL. The GIL is a problem when you're doing a lot of interpreted code. If you're doing a lot of interpreted code, you're gonna go slow. It doesn't matter. 8 hours divided by 4 cores is still 2 hours way too long, right? I'm not gonna wait for a matrix multiply. I'm not gonna write a multi-threaded Tableau-based matrix multiply in pure Python and expect it to be anything but an exercise in like, oh boy, I wrote that. It's still gonna be slow. Right, so if you're in the interpreted Python, you've already made the choice to be slow. You've made the choice because now you can be flexible, you can hook together other things, but you're just, if you expect it to be fast, you're wrong. And if you expect it to be fast because now you've got multiple cores, you're wasting the cores. Use them somewhere else, right? Figure out where your code is slow. Figure out the parts that you can speed up, and that's what this class is more about. Right? So if you're doing interpreted code, you don't care about performance. That's the statement you've made, right? If you care about it, maybe you should be working in something else, right? Maybe maybe you should be in an entire other language. Python has very good strengths. Speed is not one of them, right? Now, it's very easy to stick it onto something else that's fast, and that's where it comes in. All right. I like what David Beasley's talks in general are just pretty good. I mean, some of them are hit or miss, but his stuff on the GIL, where he digs in deep and says what's going on, is pretty good. And there's led to some changes in Python. So one place that Python really shines in general is, okay, I've got I want to serve multiple I/O requests. I want to do web serving, and I want to have multiple connections open and deal with these. There's some excellent tools for that. They used to interact very badly if you also had compute in there. But in the 3.plus series, a lot of this has been addressed, and so it's gotten better for that. So it's playing more to its strengths. It's still not perfect. That's fine. All right, now we're gonna get really opinionated. All right, more about this. All right, and this is important to remember for this class, and anytime you're working in any language, right? This is not just about Python, but this is why we don't care, right? Back in '74 even, when compute was a rare resource, and still today, don't optimize early. Make it work early, right? Whatever your favorite language, make it work in that, and then if it's not fast, put it in another language or figure out how to make it faster. Right? 97% of the time, don't worry about optimization. Find that 3%. 3% is like, those are numbers from Knuth. 3% is you're gonna go into your code. 97% of it, it just doesn't matter. It runs once. It loads the data. It talks to the user who is just infinitely slow. Parts of it, matrix multiply, image processing, things like this, that's where you optimize. But make it work first. Find where it's broken, where it's slow, and fix that. All right, where do I get my opinions? Why do you care? Well, you're in my class, so you have to care a little bit. So I worked for like a decade right out of high school in industry. I worked on like all kinds of languages and graphics applications, mostly graphic stuff. Did my PhD in 2001, and then I've been in academia since 2007. So that's a warning flag. Like, my real experience ended around 2001, right? I've worked with industry since then, and I've done some large projects, but pretty limited. So, Swift, I'm like, oh, that sounds cool. That's what the young kids are talking about these days. But I've worked in a bunch of different languages. I worked at a Lisp company for a while when they still exist. I worked on Dylan at Harlequin, which is a very interesting language, which is kind of like halfway between Python and Lisp. And so you can imagine what that was like. It didn't have parentheses, so I heard about Python in '97, actually. And ignored it for 7 years. You know why? I was like, indentation, what? No, that's crazy. That'll never work. And really, I rue that. It would have been useful for me. There was a lot of coding that I did in MATLAB, years I will never get back. Sorry, Mr. MATLAB. It's okay. I mean, I worked on a large project with like GUI, like a huge user interface in MATLAB. Yeah. Not. It's fine. It's not the right language for GUI tools, believe me. All right. The other thing is, this is what I've learned, and I actually steal this idea from someone else, but it's really accurate. This is the sort of software engineering the model. I'm going to hook up this tool, especially in a class, these days, where you're taking you take existing libraries or existing tools. You take Spark, you take a web crawler, you take something else, and you glue them together, right? I'm going to crawl the web, I'm going to pass it through Spark, I'm going to cull images from something, I'm going to do this and that, and I'm going to produce an answer, right? And people have this idea, okay, I can take all these pieces that exist, all this existing code, and hook it together into something cool, right? That's very common these days. If this, then that. You can do it in your web browser, right? That's the model. This is the reality, right? These tools are great, but the pipes, like hooking this to this, like this writes out JSON, and that reads in HDF5, and this one's that. And the pipes are easily the most work here, right? You can spend weeks trying to get formats to match. And in the bad old days, Perl was your choice, right? Now Python is the magic here, right? In Python, I can take an image recognizer running on a GPU, just blasting, crazy performance. I can cull images from Instagram using their streaming API. I can store things in a MySQL database. I can serve cat pictures, instantly from Instagram, and I can do this in a couple of hours, right? It's not that hard because it's an excellent, excellent glue language. That's another reason we like it for this class. And you may like it for that, you may not. OCaml, not a glue language, right? It's fine. It's not its strength. Python is just loves to, it's just promiscuous. It's just like, I love Spark as much as I love, HDF5, and I love the Twitter API, and they're all my friends, right? If you do need performance, this is the direction we're going to go. Python, NumPy, Cython-C, PyCUDA. If you need performance in Python. If you don't want to leave Python. I like my little Python world, so I do this.
Another reason I like Python, I'm not a computer scientist, anywhere near one, but it gives you a level of abstraction so you can concentrate on your problem instead of how do I write. I'm sure C or these other codes are great, but I don't have time to worry about that.
Right.
I have to worry about collecting data or whatever else, understanding some complicated system there.
Also too, so garbage collection, a pseudocode-like format. These also make it easy, right? When you've used C or C++ for a long time, then these become also second nature, right? And it doesn't become as much of an issue. But when you're approaching it, Python is an excellent learning language. So, yes. Also, this is also a really good point. All right. Supposedly, now I'm not going to be opinionated. Supposedly. All right. Sorry. Let's not go into that yet. More thoughts. Python, the GIL, whatever. We're good? I also want you to understand, why am I forcing to use Python when there are such better languages out there? So there's still locking. Still every 500 cycles or whatever of the bytecode interpreter, it locks and unlocks. Well, it just checks. It's a slight overhead. It can't, well, it can sort of, yeah. So the check is fast. It doesn't affect it too much, but it's still, it's not a major cost, but there is a small cost associated with it. And some of it, and it's also because of the way things get structured. a lot of the functions don't assume that they have the GIL coming in or something like this. So the code gets structured in a way that actually adds some overhead just because it has to assume that it could be called multi-threaded. So it's not a large amount, but it's still there. All right. So I want to wrap up the multiprocessing stuff that we didn't get to last time, just to show how you can, showing the map async and answering any questions about it. Okay. So when we left last time, oh, we already did the map async, right? We talked about this? I don't remember. I'll go through it again. So map async, map in multiprocessing, when you have a pool, applies the processors to each, to chunks of the list, depending on what you set your chunk size to, and then returns the result in order. Map async doesn't do this. So map will hang until the result actually occurs. So if it's a long computation, even across multiple processors, you wait for it. Map async will return immediately. It gives you a map result type, which is basically a promise of giving you a value later. It has this should be with a get method. So when you call get, if the value is already computed, it returns it. If it hasn't been returned, if the workers are still churning, then it hangs until you get a result. You can check with ready and with wait. You can say, oh, is it set? You can wait and then get, but you could also, wait is basically wait until the result is done. So you can see this. Oh, let me go back to my, there we go. Oh, maybe. All right, so I create it here. Back to the multiprocessing world. I've got a worker, it just sleeps for 1/10 of a second and then increments its value. I'm going to create a pool of 4 workers, and then I'm going to apply map async to a range of 10. And what we get back is, well, you can already see, right? I get back this map result, right? Which is basically, like I said, a handle to getting a future result. If I call get on it, right here, you see this delay? Let me increase the weight a little bit. Ooh, is that gonna be bad? No, it'll be fine. See, it sits for a while. And in fact, if I then, so in this case, down here, I do exactly the same thing. Well, it's a slightly larger range. And then I sit in loop. Ask, is it ready? If not, sleep a 1/10 of a second. Go on, go on. You can see that I'm farming this out across 4 workers. It loops for a while. And then finally, the result is ready. All right. In general, you're going to, so depending on what you're doing, map async might be the more likely choice, especially if you've got a lot of little pieces of work to hand off. Map async, you get a result back, but you can queue up a bunch of things and wait for whichever one comes back before you go on to other work. So when we're doing multiprocessing in the homework, and if you think about it for your final project, you're more likely to probably use this, depending on the actual work. All right, let's talk about communication in these now. All right, so the main differences that we talked about last lecture between threading and multiprocessing was communication, was really what it comes down to from our point of view as the programmer. Threading, you have shared memory, then you have to be careful about locking, but a lot of your communication can just be done through local variables, and it's very efficient to do this, right? That's sort of the benefit of threading, is everything's in a shared memory space, so one thread can write a value, another thread can read it and get the value immediately. In multiprocessing, we generally use pipes and queues. It's more, you hand off work rather than sharing memory. You talk through messages. It's message passing versus shared memory, basically. And there are 2 primitives for this. There's the pipe. Well, they're both interprocess. They're both first in, first out, right? They're in order things. The pipe has 1 input, 1 output in terms of number of processes that should access it. It's not multiprocessor safe for multiple writers. So this one might be, I have the parent process. It's going to spawn 4 children processes. It's going to use pipes to talk to each one. and maybe have a pipe going the other direction. But there's not going to be multiple things trying to put items in the pipe or read them out of the pipe at the same time. Queues are like pipes where everyone can put things in and everyone can take things out. And it's multiprocessor safe. So it's like a shared pipe. So sort of a heavier duty with basically it's like a pipe, but it's got some locks on each side to make sure that people don't access it at the same time and break it, okay? And that's more commonly used. It's slightly, depending on, again, the application. There's some overhead to the queue that's not present in the pipe, but it's safer to use. And also, it can be simpler in a lot of ways. So here's an example. All right, so I'm going to post these IPython notebooks, but be aware, especially with the queue one. IPython is already running multiple processes under the hood and multiple threads and dealing with data being passed back and forth from the kernels to the notebook and things like this. And starting to use multiprocessing and processes and queues breaks it. IPython will start to crash. It's okay, it's IPython, it's not you. We might see that here if I have to reset it. Just be aware. So when you're running these, after you're done, IPython might just explode. Only for this kernel. Like the other kernels will be fine, but don't expect it to work completely. So now I've got a slightly different setup for the worker. Instead of taking an argument, right here, it takes in two queues, an in queue and an out queue. And then it just sits and spins. While in the spin, it just sits, it gets a value from the in queue, sleeps for a while just to simulate work, and then puts that value back on the out queue. So it's the same worker that we were doing before in the map. Take a value, wait, increment. Except for now, it's going to communicate with these queues. And as I said, they're first in, first out, as well as you can define that in a multiprocessing environment. But multiple writers, multiple readers. So I'm going to create those two queues, and then right here, I create the processes. And so you can see the target is the worker function, and then I'm passing the arguments, which are these shared queues defined in the global space, so that each of them has a pointer to the queue, so that it knows what to do. And then I just start them all, right? I create the list of processes. One thing to be aware of, creating a process like this does not start it. Okay, so when you do this, don't expect work to start happening until you actually call p.start. If it just hangs and you can't see your workers running, that's probably why. All right, so I do this. Now I've got my workers, they're started. They're all just sitting there waiting in the queue get, which since there's nothing in the queue yet, they're just hanging. They're just waiting there. So now I'm just gonna throw 100 values on the queue. All right. And now they've all churned through their data. They've pulled a value, slept, put it on the queue. What will I get? What is the result here? It started out, right? The input was range 0 to, basically, range to 100, so 0 through 99. I've incremented each one. What is the result? In what order? Don't know. Right? Why not? Right. Right, exactly. So there's going to be there's not much compute overhead, but there's going to be scheduling overhead in here, right? It's not, I'm not on a real-time operating system where these are going to happen exactly. It's going to sleep roughly 100th of a second, roughly. But that could have a noise up to probably 100th of a second. So when I get the result back, oh, you know what, oh no, I didn't print it. That helps. It's in approximate order, but you can see right away some of the things are not. Basically, some workers finished, put their answer back. Looks like worker, the one who pulled 4, put it back before the other one went on to get something else and got even further out of order. So this is important to remember and to be aware of. Map will put things in order, but that also means that there's some overhead there in terms of when it gets answers back from the worker, it has to store them before it can stitch them together, right? So map and map async both, when they get results, temporarily store them, then when you ask for the result, stitches it into a single list, which means if you've got a really long list of work, it's expensive. There's gonna be a lot of data hanging around there. If you've got an infinite stream of work coming, you're handling user input, you need to use a queue, but be aware, you know, if I've got a web server and it's, you know, I'm sending an image, or I've got some tool that I'm exposing to the web, and people are allowed to send, you know, pictures and say, is this a cat? And it pipes it down through my cat recognizer. Be aware that just because you said, you know, you get 2 or 3 pictures of cats, you send them into the queue, you're not getting the answer back in the same order. You need to tag them with some sort of ID or something like that, so when it comes back, so that you know who you need to give this answer back to. Right? Once it goes into the queue, who knows what order it comes out. So when you use them, we'll experiment more with this, so you'll get a chance to see it, but it's important to be aware of that. All right, let's see. Thank you. No, that leads directly into this next thing. So communication using the pipe and queues and whatever else, basically message passing interfaces, very clean, very nice. It's very easy to write safe code that way. Figure out parts of your code that are parallelizable and to hand off work to them. The problem is you pay a cost, particularly for large objects. Serialization, or also known as marshalling, depending on which background you're from, is quite expensive. You must take the Python objects, right, which are stored in local memory and are just pointers and values, and turn them into something that can be communicated to another worker in another address space. And so you basically convert them to byte strings using cpickle or using pickle or something like that. Pickle is the Python serialization format. It's not super fast. It can be quite expensive. Doesn't involve usually compression, things like this. And then the worker has to then read that back out. So if you're passing images around, for example, that's expensive. It's almost better to actually pass around file names. Pass a small file name, have a shared file system, and then read the image directly. Transport costs as well. Right, you're going to pay the overhead of writing something across a socket or across something like that. If it's a large file, that can be significant as well. And then there is actual locking. So there's okay, suppose you're not sending big data, and you're not doing a lot, you know, if you break up something with not a lot of computation into multiprocessing, your overhead goes up, right? If you can't send the workers enough work to justify the cost of locking and communication and stuff like that, you're just gonna spin trying to pass things into the queue and out of the queue, and waste all your compute time communicating instead of computing. So be aware that if you've got something that's, if you've got a problem that is easily parallelizable, but not easy to break up into chunks that are big enough to hand off to another worker, then you need to do threading. If it's big chunks of something that's very easy to pass around, heavy computation, without a lot of data cost, then multiprocessing is much better. But this is the balance you have to be aware of. So we said, you know, multiprocessing share nothing, threads share everything. Not actually true. I don't know what the support like is under Windows, but I think it exists there as well. It's actually possible to share memory between processes on most modern operating systems. I think all modern operating systems, basically. You can use these multiprocessing value, which can just store a Python object. You can use multiprocessing array, which can give you a block, and you can bash that into a NumPy array even. It works, but then you need locks. One common way actually is, okay, back to that image processing example. I don't want to pass an image to another worker, but there's nothing that says I can't put it in shared memory. pass a pointer to it, or just an offset to it in some shared memory that all the processes see, and let it work on it. And there's basically no cost to shared memory under Unix systems. I can't say about Windows. The mapping is not that difficult. It just feeds into the same sort of memory mapping and virtual pages and things like this that is already there for the existing system in the OS. So it's possible. It can be beneficial, right? Then you don't have as much locking. You don't have to deal with threading. It's sort of a best of both worlds almost. But you do need to be, it's sort of a share a little bit instead of share nothing. All right, that's it for multiprocessing. Questions? It can. And then you can get into the manager, which I'm not going to talk about. It's in the multiprocessing. Some people ask questions about it. You can use multiprocessing across a cluster, and then marshalling and communication costs go way up, and you don't have access to shared memory. But it's possible. Again, it's possible. It's not heavily optimized. This is not a case. If you're doing multiprocessing work, then maybe you want to find something like Hadoop and some sort of framework underneath that is optimized for cluster work. Anyway, does that answer? Okay. So if you want to read about the manager, some people pointed it out in the guild discussion. It's in the multiprocessing docs. It's not complicated. It basically wraps like an object and provides locking access to it. Oh, in IPython? No. Don't use multiprocessing in IPython if you're trying to do work. Use IPython's built-in one, because it'll work and not crash. If you start using multiprocessing heavily in IPython, then it will start to explode when you try to reset your kernel or things like this. It'll just die. It was more just to show the examples. We're not going to talk about that because that's more an IPython specific thing. Anything else? Any more comments on the guild? No one wants to slag Python? It's your last chance after this. No. Oh, yeah. MPI is supported in Python. There's MPI Pi. They used to teach it in this class, MPI. I decided not to this year because it's got a fairly limited application. Like, MPI is very good for some problems, and people that use it for that problem, it's very good, but you almost have to build a cluster that supports MPI to use it well. That's not strictly true, but it doesn't generalize, is my feeling. But it's the cases where it's good, it's very good. Okay. All right, see you Wednesday.